let's talk about this molecule right here. So this is nickel cyanide. So first off, nickel, you should have noticed, is a metal, and then cyanide has the formula that looks like carbon, triple bonded to a nitrogen, double bonds here on the carbon, because carbon likes to have 4, obviously, and then you've got a negative here. Well, if carbon likes to have 4, it obviously wants to donate its electron pair to something, and in this case, it donates it to the nickel. So to begin with, let's first think about what then is the charge of nickel. So if you have 4 cyanide groups, that means you have this times 4. So therefore you have a net negative charge of -4 on this whole molecule. Which means in order for the whole molecule to have a -2, what must nickel be? It must have a +2 charge. Nickel +2. Then we added on 4 cyanides to it, which have a negative charge each, to give us, and of course it's going to be an equilibrium. And there's going to be some that are going to be formed. Sometimes it'll break back apart and dissociate because this is going to be an aqueous molecule. And then it's going to form this nickel cyanide complex, we will call it. So to begin with, when we're thinking about this, what makes it so easy for nickel to bind with cyanide? Well, nickel is what's going to be called a Lewis acid, because basically by having a 2+ charge, it has a region, if you will, that is going to be positively charged, which is going to make it attract these Lewis bases very easily in solution. So a Lewis base is our cyanide, and this is our Lewis acid. And I do recommend going back and reviewing what those terms meant from the Gen Chem standpoint. From this standpoint, we're also going to say that when this right here binds with the Lewis acid, it's going to be called a ligand. Another way of thinking about these is these are my electron pair donors. All right, also the complex, so the bond between nitrogen, or in this case, sorry, nickel and cyanide is going to be called a coordinate covalent bond. And this is just a little bit of definitions, if you will, and the idea is that when these cyanides binds with nickel, both of these electrons are going to come from the same molecule. It's not that nickel has one electron and carbon has another one and they form a bond, and that would be a true covalent bond, because covalent bonds, remember, are shared. But these aren't shared. This is carbon is the donor of both electrons to the nickel, so therefore instead of it just being a covalent bond, it's called a coordinate covalent bond because both electrons came from your ligand. So there's a lot of workup to describe one molecule here. But what does that have to do with equilibrium, which is what we've been discussing in class? Well, first off, this down here, this nickel plus our 4 cyanides, this is typically not going to be like what you've got of an equilibrium constant. What I mean by that is we have a new equilibrium constant we're going to talk about now. So K is actually called a stepwise formation constant. Okay, and the idea is it's called a stepwise because typically you wouldn't think that all 4 of these cyanides would come and surround the nickel all at the same time. So if you have like a 1 nickel 2+ atom in solution, typically you're going to have a cyanide that's going to come in and say, hey, can I bind with you? And form a coordinate covalent bond. And then another one might come in. But typically these do not all come in all at the same time. And so because of that, when you're really dealing with the Ks that we've dealt with before, you're talking about what happens in a single step. Okay, so it can bond here. There's a K associated with this reaction. And then whenever you bond another additional cyanide molecule to the nickel cyanide complex that's already formed, it's going to get a new K, and so on and so forth. So these are called your stepwise formation constants, and that's because you're adding one ligand in each reaction or step, however you want to call it. Okay, so now we're going to get a new equilibrium constant, that of beta. Beta is called our cumulative formation constant. And what's going to happen is a cumulative formation constant is one where you have added multiple ligands in a single reaction. So we're going to add a cumulative number of ligands in one reaction. Or a total number would be another way of putting it. Total number in one reaction. Okay, so these are the definitions, and so I just want you to know that K and beta are both equilibrium constant. You treat them just like we do all of our other equilibrium constants, where you have your products over your reactants, but one is referring to a stepwise formation constant, and the other is referring to a cumulative formation constant. So let me show you some examples of that. Here you can see nickel bonding with cyanide to form a nickel plus a cyanide. Notice you got to equal out your charges, so a 2 plus and a negative 1 gives me just a plus on the outside. This forms this complex here. And since this occurred in a single step, this is a stepwise formation constant. So is that a beta or a K? And you should have said a K. So each of these reactions are going to be Ks, meaning I added one cyanide here, I added one cyanide here, I added one cyanide here, and each cyanide, I'm taking whatever my product was, and I'm saying, hey, if this solution exists in solution, it's +1 charged. So if there's still cyanides remaining in solution, odds are this 1 plus is going to find a cyanide that's in solution, and it's going to bond with it. It's going to form a new complex. Now, if there are any more cyanides, it can attach to it and then form a new complex. And then if there's still more cyanides, we can attach and form the new cyanides in another step. And so that's why all of these are now called my stepwise formation constants. Those are all given Ks. But if we look, we could do this in a different way. Whereas instead of adding just one, so individual itty bitty one steps, we can add them all at the exact same time, like here, where we've got nickel plus 2 cyanides gives me nickel cyanide, and this is beta 2 because this is where I'm adding 2 of them. Here, 3 cyanides, beta 3. Here, 4 cyanides, beta 4. So these are my cumulative formation constants. So if you notice, still, the equations, the expressions that relate the concentration of the products to the concentration of the reactants are still written the same way as all your other equilibrium constants. They're still written as products over reactants, and if there's a coefficient in front of it, it becomes the exponent. So look through here and just kind of see if you understand what the difference is between writing a beta and a K. So also on here, I've also included the KSPs. The KSPs are the same. So typically you'll start out with some solid that you put in. The first step is dissolution. So the nickel and the cyanide break apart. But once they're broken apart in solution, do they stay together? No. Okay, and so we'll talk about this, and we probably have already talked about this a little bit when we discuss barium sulfate. So whereas you might think that you only have one option of what your product is, you actually have many different species present in solution. You have a lot of nickel, you have a lot of cyanide, and then all of these complexes also exist in aqueous solution. And so it's a question of which species has how much of it is present in this form, etc., because that might have a big effect for how you're able to analyze the concentration of the metal, in addition to what the effects of it are in whatever it is that you're studying.